In this video, I will be covering the mechanism for the benzylic bromination that you are performing in the laboratory today. One of the chemicals that you will be using in this lab is called ABCN. The purpose of using ABCN is to initiate the free radical reaction. This is the structure of ABCN. Now, what ABCN does when light enters this reaction is it allows a homolytic bond cleavage to occur. And this is going to happen between the carbon-nitrogen bond, resulting in the formation of nitrogen gas. And this will exit the reaction container and will cause this reaction to be irreversible. And this is how we actually initiate the reaction. Once the reaction is initiated, this new species will then react with another chemical in the solution called NBS. And this is the structure here of the NBS molecule. Now, as this continues to react, this radical needs to find something to react with. And it will actually come in here and remove a bromine atom. And it's only taking one of the electrons in this bond. The other one will go back to the nitrogen. So that over the course of this step, we prepare another radical. This radical is special because it is very similar to an allylic radical, meaning that it will have resonance stabilized character of this radical through not just the nitrogen but through the oxygens as well. And so what I'm going to do right now are draw some of the resonance arrows. These aren't necessarily the mechanism arrows for this reaction. I'm going to draw the other species and then I will put in those arrows for you. Okay, so these are the resonance structures, and this is why this is a highly stabilized radical intermediate. Now I'm going to draw in those arrows for you to get from one to the other. So you actually break the pi bond on the adjacent atom and form a new pi bond. And as you can see, then the radical goes up onto the oxygen. We can also do this from the other side. If you wanted to have the radical come in and form the double bond here, you can get to this structure over here. So those are just resonance arrows. They aren't necessarily mechanism arrows. But the point is you have a resonance stabilized radical, and this is going to help stabilize the system to some degree. Once we have this radical, we're going to be able to do some propagation. And we want propagation to occur with the molecule of interest that we have, which is the paratoluic acid. And this is the structure of the paratoluic acid. Now what this radical is going to do at this point is remove a hydrogen atom. We're not after a proton. You have to remember you're dealing with radicals. And you're going to remove a hydrogen atom from a benzylic position. This is important because the benzylic position is sp3 hybridized, and by removing the hydrogen atom here, we will be able to initiate the formation of a resonance stabilized radical through the conjugated pi system of the ring. And I'm going to show some mechanism arrows to show you how this is going to occur. So you come in here and you are going to remove the hydrogen atom. The other electron stays with the carbon. And this will help us make one of the products of this reaction, succinimide. We will talk about what happens to the succinimide towards the end. So I will come back to this molecule that we are forming right now, the succinimide. The other species that is formed at this time is this benzylic radical, and this is the one we're really interested in for the purposes of this reaction. So there is resonance delocalization of this radical through the ring, and I will come back and draw in the resonance arrows showing how this radical is delocalized. But it actually goes all the way through the ring system. There's actually still one more resonance structure. It's not as important as these others, but it actually comes from this one here, this next one that we're going to look at. And again, I will come back and draw in all of the resonance arrows for these species. There are 5 distinct resonance structures for this one radical, so it is highly stabilized. And now I'm going to draw in the resonance arrows. They're not really part of the mechanism, but they may help some of you understand why we go from one to the next. So these are single electron movements. And that would get you through all 4 of these. I'm going to use a different color to show you the third one in the group going to this last one down here. So another way to satisfy that. Now I'm going to focus my energy and efforts on using this particular resonance structure over the others because this is the one that will actually be the reactive intermediate. If it were any of these other resonance structures, you would lose the aromaticity of the ring or react with the oxygen, and due to experiment, they know that it never does do that. You would lose aromaticity, and that is not likely due to the energetics of the reaction. It is very specific for this benzylic position. Okay, so I'm going to redraw that particular resonance structure. Now, radicals are not stable, so they need to react. And in this particular reaction, we have a lot of NBS. So it's going to react with yet another molecule of NBS. There's always more than one of something in a reaction. And you should know this as you weigh out more than one molecule. You add quite a bit to the reaction. So here's NBS. And this radical is going to come in and abstract a bromine atom from the NBS, producing our alpha bromoparatoluic acid product that we are so interested in making. And again, this new radical that has been formed would be stabilized by resonance, as I have drawn previously here. Now, once this radical has been formed, it will go through the process all over again and react with yet another molecule of the para-bromoparatoluic acid, and we'll make another benzylic radical that will then react with yet another molecule of NBS, and this process just keeps repeating and repeating and repeating. So at the end of the day, there are two products of interest. We have our alpha bromoparatoluic acid, and we also make succinimide. These are the two products that you will have at the end of your reaction after you've refluxed for half an hour. And if you've looked at your lab procedure, you know that you will then need to filter the solution. The two solids that you will be collecting will be these two molecules. Once you have filtered them, you will then take that white powder that you have collected and add it to a beaker and add water. The reason that you are adding the water is so that this particular molecule, the succinimide, dissolves in water. It is a water-soluble molecule since it is hydrogen bond capable, and it will dissolve in water. Whereas our other product, the alpha bromoparatoluic acid, is not water-soluble, so it will stay as a solid in that beaker. And when you filter the second time, you will be able to collect this solid, and the succinimide will go through the filter since it has dissolved in the water.